Okay, big things are happening today. We're doing PD, controller design. It is our last day of class. We got lots to do, okay? So we don't mess around in this class. Lecture 6.6, when we do mess around, we also do other stuff. Okay, lecture 6.6, proportional derivative or PD controller design. So thus far, our designs have been restricted to the closed loop pole locations on the original root locus. Remember, P control just allowed us to move our closed loop poles along the root locus. So if our root locus didn't go through the closed loop pole location we desired, we're screwed, right? We couldn't do anything about it. But we're going to do something about it today. We could add integral or lag compensation for steady state error performance and vary the gain for transient response performance. But what if the desired closed loop poles, P1 and P2, are located off the root locus and the root locus doesn't intersect those locations that we have? So for instance, we could have a root locus that doesn't go anywhere near our desired closed loop pole locations due to the transient response requirements or due to maybe even the stability requirements. So we're actually very interested to figure out some way to move that root locus around, and not just around anywhere, because, I mean, just moving it around randomly isn't going to help us. We need it to go through a specific location. That's what we're going to do with PD control. We're going to use derivative compensation to move that root locus to intersect any point in the plane that we want. Okay, that's the goal of what we're doing today. So among many possible methods to address this, we pursue the following: a derivative compensator with zero location ZC chosen such that the root locus intersects that desired closed loop pole location P1, 2 with the form some gain and then some zero. Okay? So where the gain is K and the zero is ZC. This compensator is called derivative because its primary effect on the overall controller's operation on the error, E, is a new factor of S, yielding a scaling of the term S, E of S, or in the time domain, that's just a time derivative, right? So that's why it's called a derivative compensator, because it takes that time derivative. So this compensator is the way that we'll move the root locus around in a way that we can predict where it's going to go. Not just move it around willy-nilly. If we add a zero in there, we know it's going to mess with the root locus, but we want to do it in a way that's actually effective for getting the performance we want. The effect of this zero is to pull the locus toward it, okay? The locus is attracted to zeros because the root locus branches start at open loop poles and end at open loop zeros, right? So we put in an open loop zero, it's going to attract the root locus to it. So consider the simple plant of figure 6.8. Here's the root locus in figure 6.8. This is the open loop, an open loop pole pair, one at -1, one at -3. And we can adjust the gain all we want, but we're never going to be able to leave this locus, right? This branch. And say we wanted to speed up this response, okay? We wanted to decrease the settling time. We know that decreasing the settling time is to move that closed loop pole location leftward, right? But you can increase the gain all you want. You're still going to stay on this vertical asymptote. Never going to leave it. So we need to bring in a zero compensator, right? We need to move that root locus. We want to pull it to the left. So let's actually look at what happens if we try out some different compensator zero locations. So if we put that compensator zero out at -10, we're going to have the locus pull over leftward, which is good. That's what we want, right? And then come into the real axis. One pole goes that way, the other pole goes that way. And we can adjust the gain and get anywhere on that locus that we want, which is great. If you change that zero location, it changes the diameter of this circle, right? Which is kind of nice to know. Down, down, down. As you approach more and more, that circle gets tighter and tighter until you cross over, and you can even go the other direction. So it turns out that we can actually have locus anywhere in the plane that we want. If we choose one point, we can specify that 0 location accordingly to make it go through that location. Okay? So if you include negative gains and positive gains, you can go through any point in the whole complex plane using a 0 compensator, which is awesome. But if you're just guessing and checking, that's not going to do it for us, right? What we want is to have some point in the plane. Say that point is like, like right here, and we want to say, okay, I want my locus to go through that point. Okay? I want locus to go through that point in the complex plane, and therefore the question is, what ZC is going to correspond to that? I mean, in this case, I drew it on the locus at -10, so that would be -10. But another solution for ZC might be required. So that's what we're going to do in this lecture. We're going to derive an expression that always gets us that location, gets locus going through that location. Okay, so very good. Good. A way to approach designing a controller for a plant G with a derivative compensator C is to consider the compensator zero's effect on the phase criterion. Remember, the phase criterion tells us one of the two criteria that we have for when we have locus, right? So the phase criterion can be used here. And it must always be satisfied at points on the root locus. So we have that the phase of the open loop transfer function, which is G, and then we also include the compensator, C, equals pi. I took out the gains. The gains don't affect the angle, right? Gains don't affect the angle, so we don't need to worry about the gains. And we say it has to be equal to pi. That's actually, it's pi and then 2 pi modulo of pi, right? So pi, 3 pi, 5 pi, 7 pi, etc. You can go 2 pi more always. So I suppressed that 2 pi modulo in here just to make it a little simpler looking, because, simple is better usually. So this is our equation that we're going to use. And our goal with this equation is to back out what should my 0 compensator be in order to have locus at a specific place in the plane psi. Okay, that's what our goal is using this equation. So we want to solve for what that 0 compensator location should be. Okay, so in order for a desired point S equals psi to be on the root locus, then we have, get my notes here. Oh yeah, back of a page, that works. We have that the angle of G of psi, C of psi be equal to pi. Okay. So this is the angle criterion applied to the point psi. So this has to be true for us to have locus there. And that means that we can recognize that the angle here, the angle contribution of each, it's a summation, angles sum. So we have G, the angle of G of psi plus the angle of C of psi equals pi. And we can solve that for the angle of the compensator. So the compensator angle contribution can be found by simply subtracting the angle of G of psi from both sides, like that. And if we look at what is the angle contribution of the compensator, it's just going to be the angle contribution of the 0, right? Psi minus ZC, the 0 contribution, equals pi minus G of psi. So we call this angle the compensator angle. So let's think about this geometrically for just a moment. We have some point psi, some test point that we want our closed loop poles to be at, given some transient response and probably stability design requirements, right? We want it to be stable, so we want the psi to be somewhere in the left half plane. We want certain transient response requirements like settling time, overshoot, peak time, etc. So we want psi to be, say, right here. Psi. So we want to know where to put that 0. It contributes to the angle criterion, this angle, right? The angle that goes from ZC to psi. In other words, the angle of psi minus ZC. That's what we're solving for here. First of all, we need to know what the angle contribution it needs. And then once we know the angle contribution, we'll be able to find out what the value of ZC is. So that's what our goal is. So we say, okay, we're going to call this the compensator angle and give it the symbol theta C. So this is theta C in our case. So this is just an example of putting our psi out there somewhere. And so all we need to know is what theta C is. And we've found out what it is. It's this pi minus the open loop or the plant transfer function evaluated at psi. Okay? So that's pretty easy to do. You can just evaluate a transfer function at some test point easily enough. And if you are to do the little bit of trigonometry required, it's a very simple trigonometry, required to figure out then what ZC must be in order for it to contribute this angle, theta C. It's pretty straightforward. You can just do the little, it's essentially a right triangle contribution. Figure out what ZC should be in order to make theta C what it is. And you get that ZC has to be, well, this is a solution for it. The real part of psi minus the absolute value of the imaginary part of psi divided by the tangent of theta C. Just a little bit of trig there. And what's nice, this expression actually does not show up in the Nice textbook, and I highly recommend you use this, though. The Nice textbook does a sort of ad hoc every time using different, just like doing the trigonometry each time kind of by hand. It's okay, but it's kind of nice to have a formula that's going to work on multiple problems and not just in a special case. So I recommend using it. Good. So we've figured out what theta C is from this expression, and we figured out what ZC is from this expression. So we know what ZC is in order to make our root locus go through a specific point in the complex plane, psi. That's what we want it to go through. We can make it go through that. It's just sweet. So now we're going to define the design procedure for a PD controller using derivative compensation. Thank you. Almost dropped the ball there for a second. A little slow.
I had a little Swedish fish stuck in my teeth.
Okay. It wasn't the rum and coke then. Okay.
No,
Okay.
strictly Swedish fish.
Strictly Swedish fish. That is a tongue twister. Yeah. Good for you. Okay. The following procedure provides a starting point for proportional derivative controller design. Let's assume the transient response spec is such that we desire a closed loop pole to be located at S equals psi. So this is where we want one of our closed loop poles to be at S equals psi. We can only specify one, though. We can't specify multiple locations. We can only choose where one of the closed loop poles is going to be. The other ones are just going to be wherever they end up on their other branches, right? So there we go. So step 1, design a proportional controller to meet transient response requirements by choosing a gain, K1, the dominant closed loop poles to be as close as possible to psi. So you try to do it with just proportional control, right? And assuming that we're going to be doing PD control, we're probably not going to be able to get there, right? If you can get there using proportional control, you don't need to have a derivative compensator. Okay, step 2, include a cascade derivative compensator of the form K2 equals S minus ZC. So you need to have another gain, you need to have a 0, okay? Where initially we just take K2 to be 1, we're going to first choose ZC using the little method that we just developed in the lecture above, and then we'll use root locus to determine K2, the appropriate K2. Okay? Good. So we need to choose ZC such that it satisfies equation 614, which is right here. I repeated the two formulas that are very important. The first formula is you can calculate theta c by evaluating the transfer function at the test point and subtracting that from pi. And remember, there's a 2 pi modulo on here too, so you might need to add 2 pi or subtract 2 pi. It sort of depends on which wrap you want to be on. And then your ZC then, you can compute, since you know theta c and you know where your test point is, you can compute what your ZC should be. So there you go. That's step 2. So you did derivative compensation. But you haven't, so step 3 is to do the new root locus to determine K2. So you determined ZC in step 2. Now you're going to determine your K2. You gain K2. So ZC was this part of the compensator. K2 is the second part of the compensator. So do that in step 3. And then construct the closed loop transfer function with the controller. You just cascade them together, K1, K2, S minus ZC, and you've got your controller. Then simulate the time response to see if it meets the specs, and then tune accordingly. So usually you choose the location of psi based on the second order approximation, okay? You aren't guaranteed that you're going to get the performance you expect out of that closed loop pole location psi. What you are guaranteed by this procedure is to get a root locus that goes through the point you specified, your psi, okay? So that part is guaranteed. The performance of your closed loop system is not guaranteed because you probably used the second order approximation to come up with that performance, or that test point location. So once you get that test point location to be on the root locus, once you've moved that root locus using your derivative compensation to go through your test point, doesn't mean that you're therefore going to get the performance you were expecting or you were hoping for. You still might have to adjust gains accordingly, or you could move the zero compensator around as well. Okay, so that's the procedure. Let's do a design example, okay? So let a system have the plant transfer function below. So it's got 3 poles. It's a third order system. And we're going to design a PD controller such that the closed loop settling time is about 0.8 seconds and the overshoot is about 15%. Okay? Now, yes?
For about, like, on the exam, or would you be, like, less than 16 and greater than 14, like, as long as it's, like, you would round to 15 is close enough, or what would you consider?
Yeah. I mean, if you're within 10% is pretty reasonable for this context. I mean, in a real application, you're going to want to go back and go through it and multiple times and all that, make sure you really tune it up nicely. But yeah, on an exam, if you do the correct procedure and you get within 10%, that's pretty good. Especially, I mean, if you get within 10% the first time round, I would say go back once and tweak the gains and see if you can get a little closer. But once you get within 10% and you've done one iteration through, like, that's probably good. You don't need to keep going. I mean, keep going if you're not within 10%. But like one iteration, if you're within 10%, I'd say that's probably good. Yeah. Good question. Determining psi. So that's the first step, because we're going to determine where we want our desired dominant closed loop poles to be, because that's where we are going to want the root locus to go through, right? So you got to find where that is first. So we use MATLAB for the design. First, we must determine what the specified transient response criteria imply for the locations of our closed loop poles. So that's what we need to decode first. So let one of the desired let the one of these desired closed loop pole locations be psi. So remember, we can only specify where one of them is going to be. The other ones are going to be wherever they are. If you're going to specify psi to be a complex number, there's always going to be a pair. That's the one that's going to be off the axis and mirrored about the real axis as well. And then the other poles are going to be wherever they end up. Okay? So we get to only specify one, psi. The transient response performance criteria are given in the problem, right? 0.8 seconds and 15% overshoot. So the second order approximation from chapter 3 tells us that the settling time spec implies a specific real part of psi and the overshoot a specific angle of psi. So those are the two things that are specified. The real part is found from the expressions below here. So this is from the settling time requirement. This is from our nice second order pole pair geometric interpretation with the second order parameters. Negative zeta omega n is the real part of psi. That was one of the parameters we drew on that plot. So you can combine those together and get that the real part of psi should be -4 over the settling time. This is a general result. Okay, this doesn't just apply to this problem. This applies to any problem where you have a settling time specified. That tells you what the real part of your desired closed loop pole location, your test point, should be. Okay. The angle is found via these equations. So the damping ratio is related to the percent overshoot. This was given in chapter 3. And if you go ahead and this was given as one of the geometric interpretations. And so what we can do is use these geometric relationships here to solve for the imaginary part of psi, okay? Which we need to know too. We need to know the real part of psi, we need to know the imaginary part of psi. So we have two expressions. I wrote it out in two different ways. So you can either use the damping ratio or the percent overshoot. And you also need to know what the real part is as well. So you got to find the real part first, then you can find the imaginary part. So in the final analysis, the desired pole location, psi, assuming the second order approximation is valid, is given by the expression below, which is psi is equal to something that depends on the settling time and the percent overshoot only. Now, this expression does not show up anywhere in the textbook, to my knowledge. This is a really nice result, and it holds beyond the scope of this problem. So anytime you want to find out where your closed loop pole location test point should be, based on these two performance criteria, the settling time and the percent overshoot, you can use this formula. It's a pretty nice formula, and the way that the textbook does it is always using this trigonometric ad hoc process, which is okay, but I get really annoyed at that kind of design technique. When you're going to do a lot of these design problems, it's nice to have these formulas that are more general to work with. So this gives us the location of our psi if we have a specific percent overshoot and settling time that we would like to work with, which are two of the most common design criteria. Okay? It's a useful one. Good. So we define in MATLAB an anonymous function for it. So this is just equation 623 written in MATLAB anonymous function form. And then we evaluate the function for the specs that we were given, and it tells us that our psi, our desired closed loop pole location, is -5 plus j 8.28. Cool, right? That's where we want to be. Now, we're going to do p-control. Let's see if we can get to that test point using p-control. So define our open loop transfer function using ZPK. Had those three poles, -2, -6, and -11. Open a figure, use our locus, gives us a figure that looks like this. So our test point was -5 plus J8, right? J8 point something. So this is our desired closed loop pole location. The root locus is over here. Not going to do it, is it? Right? The root locus does not go through our test point. Therefore, no matter what we change our gain to, we're never going to get the performance we want. All right. So we're going to do the best we can with P control. What I decided to do here is say, okay, let's just adjust the gain so that we at least meet our spec of the percent overshoot, which is going to be 15% overshoot along this line. 15% overshoot. So I can at least meet that with proportional control, but I can't meet the settling time spec. So I'll just meet one of them. I'll do the overshoot, and then settling time we'll have to do a derivative compensator to get. Okay. So very good. Very good. So we go ahead and choose that. 240 is our gain. We form also the closed loop control, or the closed loop transfer function using the feedback here. Yeah.
For the 240, did you just find that graphically?
I just used the I just used the cursor, data cursor in MATLAB.
So you like graphed a little cursor out, like drew where.
So I just clicked on. You can, once you click on the trace, you can move the data cursor around, and it tells you what the gain is required for that, and it tells you what the percent overshoot is.
Oh, so like you just went to 15% and then it was line up. You didn't have to like trace.
I didn't have to trace at all. No, I mean you can go to where it's gonna you look like it's gonna be close. You click there, and then you can adjust it using the up and down arrows to get closer and closer to it.
So
Yeah.
how accurate does that have to be? 'Cause, like my overshoot goes from like 12.1 and at 204 to an overshoot of 15.8.
Usually, I did show you the idiom to add in more gain values if you want, but oftentimes, especially if you're going to add a compensator in there, probably not a big deal. Just be close. And then when you add the derivative compensator in there, you're going to adjust again anyways. So I wouldn't obsess, especially the first gain you choose. The next gain can make up for it. So, yeah. Good question. Sometimes it's like it jumps from, 0% to 30% on the next point, and then you're like, well, I need a little bit more accuracy here, a little more precision. Good. So let's look at what we can do with derivative compensation. So this is our derivative compensator. We have another gain K2. We have the zero location. The zero location we choose to do first. That was the next step in our design procedure. So we have two formulas. We know what psi is, right? We have two formulas that we need to plug into. The first one gets us the angle contribution of the compensator. The second one gets us what the zero location should be. And we've got theta c, this formula, pi minus, and now there are a couple nice MATLAB functions we're using here. The first one is called eval-fr, which stands for evaluate a frequency response function. It also lets you evaluate a transfer function at a given location. That's exactly what we're doing here. We're evaluating a transfer function, g, at psi. So we just plug in eval-fr, g, and psi, and we get the result to come out. And then we want the argument of it. We want the angle. Okay, so there's an angle function built into MATLAB as well. So eval-fr and angle are both built in. Eval-fr might be part of the controls toolbox, but it's in either the controls toolbox or in MATLAB core. I can't remember which, but anyways, their angle is definitely in MATLAB core. And then just subtract that from pi, and we get theta c. Then we're ready to compute zc, which is the real part of psi minus the absolute value of the imaginary part of psi divided by the tangent of theta c. And we've got ourselves a zero location. Okay? Very cool. So, turned out we needed a zero contribution angle of 67.1 degrees. And that corresponds to a zero location of negative 8.5. just from the formulas, okay? Pretty nice. You can go through the trig of that too, and that's what Nice does in the examples, which is fine too. Let's construct the compensator sans, or without, tuned gain K2 and tune it up using another root locus. So construct the compensator without the K2 gain in it. So in other words, letting K2 equal 1 for now, and then we'll adjust it using the root locus in a moment. So the 0 compensator using ZPK, stick the 0 in there. There are no poles in this compensator, and it has a gain of 1, overall gain of 1. Open a figure, do another root locus, but this time include the compensator and the original gain, and there your K1. And then we get the root locus of this figure here. So now our test point is guaranteed to be on the root locus. Mathematically guaranteed. So it's good to check your root locus and make sure it looks right, but it should be right on the money. So you can once again use the data cursor to tune your K2 to choose your second gain that corresponds to that location. But since you're guaranteed mathematically to have a root locus that goes through that point that you want, psi, you can actually just use this nice analytic expression too, which is what I do here. So K2 is equation 6.26 comes from lecture 6.1, I believe it was, which is evaluating the gains or determining a gain that corresponds to a certain root locus point. Good. So once I've got my K2, either from the data cursor or from this analytic expression, either one is fine. My compensator is complete now, so I've got K1, K2, and C without the gains. And then I've got my closed loop compensated system. So I do feedback, I use the full compensator, I use the plant transfer function, and I do unity feedback on it, and I get my closed loop transfer function, which allows me to do simulation, okay, in the next step. So our placement of psi depended on the second order approximation's accuracy, right? We know we got psi right out of the money, but we don't know if the second order approximation is good, especially because there's a proximal third closed loop pole. So there is this pole pair, but remember, we don't get to decide where this other pole is. It could be here, it could be here, somewhere along this branch, right? But it's just going to be somewhere. And -5, our factor of 5 rule of thumb for using the second order approximation is definitely violated here. So we don't know how accurate we're going to be because the psi would depend on the second order approximation. So we simulate. We do our nice step function to simulate both the PD controlled system and the closed loop system for P control. So we do both because we want to compare what the performance looks like. And then we plot them. You got to be able to plot these, by the way, on the exam. That should be part of the sort of repertoire that you have, is to be able to plot these. Good. So this is the result. You've got the P control in blue, and you've got the PD control in orange. So we definitely sped up the transient response, right? The settling time is definitely shorter for PD control. So that's what we were going for there. The percent overshoot looks to be about the same, which is because we designed the P controller to have the percent overshoot spec met, but we couldn't meet the settling time. So we did meet the overshoot, but not the settling time for for P control. Notice both of them have a steady state error problem. We have to use an integral compensator if we're going to fix that. The fact that the PD or that the derivative compensator improves steady state error is actually just an accident, okay? It could have gone the other way. And this is why when we do PID control, also we start out doing PD and then we add in an integral compensator at the end, okay? Because the D compensator, the derivative compensator, can change the steady state error situation. So we try to avoid that. Okay, good. So PD control, it definitely improved the settling time, but let's actually figure out what it is using step info. So the settling time that we got is 0.82, which we were going for 0.8, so that was pretty good. And the percent overshoot is 16.2. We were going for 15, so we're pretty close to the spec. We could probably do like an iteration of tuning to see if we could get it a little bit tighter, right? We can move that ZC around if we want, or we could tweak the gain. Those are our two adjustable parameters at this point, and you could tweak those a little bit and see if you can get a little closer. So that is the design process. Are there any questions? Yes?
It seems like you can kind of just set up a function that like started with two random points and then iterated it, and every single time kind of went to your design.
Yes, that is possible. With PID control, so there are, I mean, people have written a lot of auto-tuning algorithms that will come up with a PID controller that will give you pretty good performance just by iteratively changing it and seeing what happens. So you can do this in simulation, and you can also do this in the real-world environment too, where you can just tweak your controller gains until you get performance that you want. So that is a method so there a lot of techniques nowadays can be sort of brute forced using a computer algorithm, and knowing when that's a good choice and when it's not a good choice kind of requires that you understand what the design process was like to begin with. But you're right, you can automate this process a little bit, but I would say it's far from being a situation where like it always works every time to just put it into some like auto tuning algorithm. The performance isn't always what you want, so having insight into how it works is going to be important if you're going to be an actual control engineer. So any other questions on this? I do want to do a little demo.